Okay, thank you. I actually have one announcement first, which is on the board. Barry Mazur and I are organizing this conference, which is funded by the National Academy of Sciences for next March. And there's a small amount of information available now, but if you subscribe to this email list, you'll get future announcements as they come. And the web page at the bottom does not exist, actually, at this moment, because it's rather hard to set it up from the terminals that are available here. But by the time most of you get home to a terminal that can access it, it should be there. Okay, so back to work. And in fact, there isn't really too much work left to do. So the goal for this talk is the following theorem. Call it Theorem 1. And this is sort of the culmination of the papers of Wiles and Taylor-Wiles. And that is that if E is an elliptic curve over Q, and E is semi-stable, then E is modular. And of course, this is the theorem one wants to prove to imply Fermat's last theorem. And the attitude that you should take for this lecture is that really all the hard work has been done. We now have the tools with which, with those tools and a little ingenuity and just a little bit of playing with elliptic curves and modular curves, we can prove this theorem. So what are the tools that we now have? Well, we have two other theorems. The first, which also comes from the papers of Wiles and Taylor-Wiles, says that if, again, E over Q is semi-stable, rho E, let's see, P is a prime at least 3. And we have two important conditions, namely rho, the mod P representation on E, which I'll call rho EP bar, as everyone else has, should be both irreducible and modular. Then E is modular. Okay, so there are two rather important hypotheses in this theorem. One is that this representation is irreducible. The other is that it's modular. Being irreducible is a fairly easy condition to check in principle, but it's not always going to be true. Modularity, on the other hand, you expect is always true, but it's quite difficult to verify. So the way to proceed with this, of course, as has been mentioned several times, is what I'll call Theorem 3, which is the result due to Langlands and Tunnel, which says that if rho E3 bar, if the mod 3 representation on your elliptic curve is irreducible, then it's automatically modular. Okay, so that takes care of the difficult hypothesis for the case where P is 3. And clearly, if you want to apply this theorem with P equals 3, then all you need now is the assumption that rho E3 is irreducible, rho E3 bar is irreducible. then you know that it's irreducible and modular, then E is modular, and you're done. But as I said, unfortunately, it's not always true that rho E3 bar is irreducible, and so one has to come up with a method for dealing with the case of reducible rho E3 bar. And Wiles came up with an ingenious method. Let me state the result first, and then I'll make some remarks about it. But so the theorem that I want to talk about today which is basically due to Wiles, says that if, so suppose E is semi-stable, and there'll be two parts. First, if the mod 3 representation is reducible, then the mod 5 representation is irreducible. And second, if rho E5, the mod 5 representation, is irreducible, then it's modular. So the idea is, when you can't use 3, what can you do? Well, not much, except try to apply theorem 2 with some other prime. And so that's what we're going to do. We're going to apply theorem 2 with the prime 5 instead of the prime 3. And theorem 4 is just what you need to tell you that you can do that. So the first remark is the proof of theorem 1 from the other two theorems, namely, if the mod 3 representation is irreducible, then theorems 2 and 3 imply theorem 1. And if not, then theorems 2 and 4. And that's the proof. Okay, so we want to prove theorem 4 then. More remarks. First of all, why p equals 5? Well, as you'll see from the proof in just a minute, the proof of these two separate parts is going to rely crucially on two separate facts. For part 1, we need to know that the genus of, the genus of x0, the modular curve x0 of 3p, should be bigger than 0. So if we want to apply the argument I'm going to give you with a prime p, one needs this. And for part 2, one needs that the genus of the modular curve x of p is equal to 0. The first condition, it's easy to check, is equivalent to p at least 5. And the second condition is equivalent to p at most 5. So sort of just as with the Langland's tunnel theorem in the first place, one doesn't have too many possibilities as to where one can apply this argument. But one does have one, namely p equals 5, and it's going to work. Okay. Another remark is that we have basically proved this theorem 2 during this conference, or at least as far as a sketch goes. But a good exercise, if this is the first time you're seeing this material, is to go back through your notes and really put the different lectures together and convince yourself that you have seen a sketch of the proof of theorem 2. Because the different parts do have to be interwoven to make that work. And just one comment about that. So for theorem 2, so this was proved, I mean, you should look in the lectures of Rubin and de Chalit and Scoffe. But if you look at those, you'll see rather than the assumption that rho EP bar is irreducible, there was this stronger condition. We really want to assume that the restriction of rho EP bar to the quadratic extension that's come up several times, the Galois group over Q square root minus 1 to the P minus 1 over 2 times P, that this should be absolutely irreducible. Okay, but there's a lemma that one can prove, and this is one instance of where semi-stability makes life easier, and that's that if E is semi-stable, then rho E P bar irreducible implies this stronger condition, that rho E P bar restricted to, I think this is the field that Fred Diamond just called L. Maybe I'll call it L sub P. Is absolutely irreducible. I won't prove this. It really just comes from the group theory and what you know about these extensions. I can tell you the key fact, I suppose, where semi-stability comes in, and that is that if L is different from P, and so if L is different from P and L ramifies in this representation, so in the field of P torsion, then using semi-stability at L and thinking about these Tate curves that we've seen, that implies that the ramification is equal to P. So the is equal to P. And basically you show that if this were to fail, then the image of rho has order prime to P. So you've got great control on the ramification of that field. But I won't say any more than that. Okay. Let's see. No more. Theorem. Not quite. I want to keep the theorem we're proving visible. Okay. Okay, well, still on the remarks, as Fred Diamond said in the last talk, there is a stronger version of the theorem 1. So if you add in Diamond's result, you can prove that E semi-stable at 3 and 5 implies E is modular. And that would follow from analogs of these other results along the same lines, but it's just a little bit more complicated in that case. So let me go through the proof in the simpler semi-stable case, and if there's time at the end, I'll go back and tell you about the extra details. In this case, in any case, well, in any event, the details of the more general case will be in the write-up. The last remark is that, so the Langlands tunnel theorem, which is now hidden, is not really a theorem about representations coming from elliptic curves. It's a theorem about Galois representations. So you can remove sort of the elliptic curves, the E, from the modularity statement, well, from, I guess, from theorem 3, the Langland's tunnel theorem, and from theorem 4, part 2. So theorem 3 prime, which is what closer even to what Langland's and tunnel really proved, is that if rho bar is just a representation from the Galois group of Q to GL2 of F3 with odd determinant, so the determinant rho bar complex conjugation is -1, then you can conclude that rho bar is modular. Well, you can do something similar for the part 2 of theorem 4. And that would be to say that to start with a rho bar from the Galois group of Q to GL2F5, if you want to apply the methods I'm going to talk about today, you have to assume a stronger statement than this. You have to assume that the determinant, oh, of course, I left out irreducible here. I have to assume that the determinant of rho bar is the mod 5 cyclotomic character, and rho bar is irreducible, and that rho bar is semi-stable at 3. That will imply that rho bar is modular. What does it mean to be semi-stable at 3 when you don't have an elliptic curve floating around? It just means it looks like the mod 3 representation, sorry, the mod 5 representation that would come from an elliptic curve which is semi-stable at 3. Precisely, this means that rho bar of the inertia group at 3 is unipotent. Okay. And the proof of this theorem from the theorem 4 is, in fact, that it's not really any more general than the original theorem. All such representations will come from elliptic curves covered by theorem 4. But I don't think I'll say any more about that. Okay, so let's move on then to the proof of theorem 4. Not that one. Okay, so let's prove the first statement. So, okay, well, so what does it mean for rho, the mod 3 representation, to be reducible? That's equivalent to saying that there is that the Galois module of 3 torsion points has a cyclic subgroup C sub 3 defined over Q. So the subgroup is rational over Q, not necessarily the points. And this is cyclic of order 3. And similarly for the 5 torsion, if the mod 5 representation is reducible, that's the same as saying that the 5 torsion contains a Galois invariant subgroup, which is cyclic of order 5. Well, if both of these things happen, then we can just interpret that as a cyclic subgroup of order 15. So that the 15 torsion contains C15, which is defined over Q, and it's just the sum of C3 and C5. So it's a cyclic subgroup of order 15, and that means it gives us, since the subgroup and the curve are defined over Q, this would give us a rational point on the modular curve x0 of 15. So if it's reducible at both 3 and 5, then the elliptic curve E with the subgroup of order 15 we can think of as a rational point on the modular curve x0 of 15. Okay, so what do we know about the modular curve x0 of 15? Well, in fact, we know a lot. First of all, it has an amusing model, y squared. It's genus 1, and it has rational points, so it's an elliptic curve, and it has the amusing model y squared equals x times x plus 3 squared times x minus 4 squared. So I'm glad you're awake. But that means we know a lot about its rational points, namely x0 of 15. It's easy to check. Well, it's a group of order 8. It's a z mod 4z cross z mod 2z. And you can find those rational points without too much difficulty if you want. But if you think of it in terms of the modular curve we started with, it also has the set of rational points contains 4 cusps. If you remember, it's the open curve, if you throw away the cusps, that parametrizes pairs of elliptic curves with subgroup of order 15. If you use the full curve, then you're including these degenerate elliptic curves. And this statement tells you that of the 8 rational points, 4 of them correspond to degenerate elliptic curves. Degenerate. So what we're trying to prove is that there are no semi-stable elliptic curves with these 2 properties. And what we've shown is that at least up to twist, up to isomorphism over C, there are only 4 possible curves. Okay, well, how do you find out what they are? Well, people have computed lots of tables of elliptic curves. So you just look through these tables looking for one that has a cyclic subgroup of order 3 and a cyclic subgroup of order 5. And you don't have to look very far in this case. So from various tables, you find, I can even write one down. Y squared plus xy plus y equals x cubed minus x minus 2. Sorry. I'll be with you shortly. So one has to check that this, in fact, has cyclic subgroups of order 3 and 5, which I won't do. But if you believe that, and if you look in the tables more carefully, you can see it, then that actually produces all 4 of the curves we're looking for. So inside the Q bar points, so inside E15, we have a cyclic subgroup of order 3, a cyclic subgroup of order 5, and of course we have their sum. So if you look at the 4 curves, E modulo the cyclic subgroup of order 3, E modulo the cyclic subgroup of order 5, and E modulo the sum, this is 4 elliptic curves, not isomorphic over the complex numbers. And you can also check that each of these quotients has a rational cyclic subgroup of order 15. So that these represent represent the four non-cuspidal, non-cusp rational points of x naught of 15. Okay, you can also check that none of them, so they're all, also they're not semi-stable at 5. In fact, they have conductor 50. And only slightly more thought, well, or calculation will check that there's no twist of this curve, which is semi-stable, which is also important because the elliptic curve corresponding to this point on x naught of 15 is not unique. It's its isomorphism class over C. But in any case, these curves, these points correspond to non-semi-stable curves, and that proves point 1. There is no semi-stable curve that shows up as a point on x naught of 15. Okay. What about part 2 of the theorem? Okay, well, as Jerry Tunnell pointed out in his lectures, well, okay, so we're now coming to the, in some sense, the more subtle part. We're trying to prove that certain mod 5 representations are modular. And as Jerry Tunnell pointed out, if you want to prove some representations are modular, somehow you have to be producing modular forms. So when we started all this a week and a half ago, we didn't have very many ways of producing modular forms. Jerry Tunnell in his lectures showed how to produce some modular forms, which I'll draw in this picture as the just Langland's tunnel forms. Which were not enough to do what Wiles wanted to do. You didn't necessarily know that in this set you had produced, you had found the particular forms corresponding to the elliptic curves you wanted. So Wiles had to go through this whole deformation machinery to produce, or at least specify, more modular forms. And so I'll call these, well, I'll just say we have sitting in this collection a modular form corresponding to any elliptic curve E prime, where E prime satisfies sort of the, well, the hypotheses we're already happy with, namely that rho E prime is semi-stable and rho E prime 3, the mod 3 representation, is irreducible. Given such an elliptic curve, we've already proved that it's modular. That means we've produced somehow a modular form that we have some control over. We know how it relates to a particular elliptic curve. Now we're stuck with the problem of how are we going to show that these mod 5 representations are modular? Well, either you have to come up with a new way of producing modular forms, which is presumably hard, or you have to use the ones you've found. And the Langland's tunnel forms are not enough. They don't help you when P is 5. So what Wiles figured out how to do is how to find the mod 5 representations he was looking for inside this set. And so that's what I have to explain. Okay, so let me just write down what I just said. So the claim is that given our elliptic curve E, so I'm in the situation of theorem 4, the claim that we can find a modular form F corresponding to rho, our given representation mod 5, in the set of all F E prime, where E prime is semi-stable and rho, the mod 3 representation on E prime, is irreducible. Okay, so what does that mean? First of all, what does it mean for F to correspond to rho bar, to the mod 5 representation? Well, there is a mod 5 representation attached to F. So if rho bar, if the mod 5 representation we start with corresponds to a modular, one of these modular forms F E prime, that just means, by definition, that's the statement that this mod 5 representation is, well, or is isomorphic to the mod 5 representation attached to the modular form F sub E prime. But F sub E prime is a modular form corresponding to the elliptic curve E prime, so this, by definition, is rho, the mod 5 representation on the curve E prime. So one thing we're looking for is an elliptic curve E prime whose mod 5 representation is isomorphic to that of E. And then we have these extra conditions that the E prime we're looking for should be semi-stable and that its mod 3 representation should be irreducible. So aside from semi-stable, the irreducibility and the equivalence of the mod 5 representations are two facts that we can translate, again, into properties, well, into points on certain modular curves. And so that's what we have to do. So here the modular curve we want to consider, well, there are going to be a few of them floating around. But so the first one I want is, I'm going to call x of my given representation, rho bar E5. This is going to be what Alice Silverberg called in her lecture yesterday, well, she may have called it x, but this is the twist of what she called x sub 5 by a cocycle coming from this representation, rho bar E5. And what was important about it is that it parametrizes pairs E prime phi, where phi is an isomorphism from E prime 5, the 5 torsion on E prime to the 5 torsion on E. So the rational points of this modular curve are exactly the elliptic curves over Q whose mod 5 representation is isomorphic to the given one, except the way this was set up, we also want to say that it takes the Weil pairing, for 5 torsion on E prime to the Weil pairing for the 5 torsion on E. So to summarize that, so the conclusion is that if let me say that every point, every rational point on this modular curve, x of rho bar E5, let's say every point, and we might have to avoid the cusps to avoid degenerate elliptic curves, gives an elliptic curve E prime with rho E prime 5 bar. The representation, the mod 5 representation on E prime, isomorphic to the mod 5 representation on E. And so this is in some sense the hardest of our conditions. We're looking for such a thing. And the theorem that Silverberg proved yesterday was that there are infinitely many such rational points, because this is a curve of genus 0, and you know it starts out at least with a point corresponding to E. Okay, we want to know a little bit more than that. So let me remind you, so in yesterday's talk, one had the universal elliptic curve, W, sitting over this x of rho bar E5. And corresponding to we identify this with P1, and corresponding to a t, a rational number t, there was an elliptic curve. The fiber over t looked like y squared equals x cubed plus a times f of jtx, f4 of jtx, plus b times f6 of jt, where I guess the original elliptic curve had Weierstrass form y squared equals x cubed plus ax plus b. And f4 and f6 are polynomials with integer coefficients. J, capital J, was the J invariant of the elliptic curve E divided by 1728. Well, from this information, we're going to be able to get one of the other conditions we want, namely the semi-stability of the elliptic curve E prime. So what about the semi-stability? Well, one of the other things that Alice Silverberg mentioned, although didn't prove in yesterday's lecture, that we need now, is that if the mod 5 representation on E prime is isomorphic to the mod 5 representation on E, and E is semi-stable at a prime L different from 5, then so is E prime. We're assuming E is semi-stable everywhere, so it follows from that statement that E prime is semi-stable at all L not equal to 5. The point is you can see whether a curve is semi-stable away from 5 from the mod 5 representation, and since those representations are the same, we get almost all the information we want for free. What about at 5? Well, at 5, the simplest thing to do is just to observe that this curve is semi-stable at 5. That's just a statement about the roots of this cubic mod 5. If you pick t sufficiently close to 0, I suppose I should have also said that at 0 these are both 1, then if t is close to 0 phi-vatically, then E sub t is close to E phi-vatically. And I just mean by that that the Weierstrass equations can be made as close as you want. Then E sub t will also be semi-stable at 5. Because this is a property you can read off just from the form of the equation. How close you have to take it may depend on how cleverly you chose these, whether they're integers or divisible by large powers of p, but it's just completely not a problem. Okay. Let's see. So this remember is what we're looking for. We're looking for an E prime with the same mod p representation as E, which we can find on points of this curve. We want it to be semi-stable, which we can find by taking t phi-vatically close to 0. And we want it to be irreducible, the mod 3 representation to be irreducible. Well, that's going to come by looking at an additional modular curve, because the reducibility at 3 we know corresponds to a Q rational subgroup of order 3, and modular curves are just set up to tell you things about that sort of object. So let me draw this diagram. Here's our modular curve x of rho bar E5. Over that, I want to consider the modular curve x, well, I'll just call x of rho bar E5 comma 3. And I have to tell you what that means, because this is completely non-standard. Remember, the points here correspond to pairs E prime comma phi, where phi is an isomorphism from the 5 torsion on E prime to the 5 torsion on E. Well, the points up here are just going to correspond to triples E prime phi C sub 3, where C sub 3 is a cyclic subgroup of order 3 defined over Q. Remember where this came from. This was a twist of the modular curve x of p. So the way to think of this is that over C, so the x rho E 3 bar comma 3, the complex points will look like the upper half plane modulo the intersection of the principal congruent subgroup matrices congruent to 1 mod 5 and congruent to something upper triangular mod 3. Okay, and also there's an obvious map from the upper curve to the lower curve, which you get just by throwing away the subgroup of order 3. And so what are we looking for now? We're looking for a rational point here in a phi-vatic neighborhood of 0, which is not the image of a rational point here. Because to be in the image of this of the rational points here is precisely to say that there is a rational subgroup of order 3. That's what you want to avoid. So, without erasing what we want, so all we need is we want a rational point T that lives in, well, so it's a rational point of x of rho bar E5. We have to stay away from the cusps, which is not a problem. We have to stay away from the image of this upstairs curve, x rho bar E5. 3, the rational points on that. And we need to take t close to 0. T close to 0, where that, if you think of the modular curve, we want it to be close to the point corresponding to E and the identity map, which we're thinking of as the fiber over 0 in P1 phi-vatically. Okay, well, there are infinitely many points on this modular curve, infinitely many rational points. There are infinitely many points in any phi-vatic neighborhood of 0. There are only 12 cusps. So ignoring the cusps is not going to be a problem. The only thing you have to at least pay some lip service to is the image of this, the rational points on this curve. But in fact, that's not a problem either, because you can check quite easily from this that the genus of this upper curve is 9. And so if you're willing to apply Folting's theorem, this has only finitely many rational points. And I think we should be allowed to apply Folting's theorem because it was covered in the predecessor to this conference. I mean, in Weil's paper, as many of you know, he doesn't use Folting's theorem. You can prove this using Hilbert irreducibility in a way that would apply even if this had genus 0. So it's not necessary, but if you are willing to apply Folting's theorem, then you see quite easily that, in fact, there are only finitely many problems you could run into this way. And that finishes the proof. Okay, so that's the proof of this theorem and finishes the proof that semi-stable elliptic curves are modular. Let me just say one word about what you do in the general case and what's different if you want to prove the theorem about curves semi-stable outside of 3 and 5. Okay, so I don't want to erase this. I just want to show you sort of how these tools change and maybe address one point. So theorem 1 prime, we just want to say semi-stable at 3 and 5. And of course, we want to add diamond to here. So that's what one wants to prove. And then what the tool you need is, I mean, it's basically the same theorem, except instead of assuming that it's semi-stable, you just assume it's semi-stable at P. And now you have to be careful and put back in the condition that the restriction to that field L sub P is absolutely irreducible. Okay, and so that's what the theorem that Diamond proved in the previous lecture. The Langland's tunnel theorem doesn't change. And now for theorem 4, let me write theorem 4 over from scratch. So the analog of theorem 4, which still is basically Weil's technique, it's just used in a slightly more complicated way. The first part is that if, how do I want to say this? If rho E3 bar restricted to, well, the Galois group of q squared to minus 3 is not absolutely irreducible, then the restriction of rho E5 to the appropriate field is now q square root of 5 is absolutely irreducible unless, well, except for 8 possible. Well, I mean, I shouldn't say possible, except for an explicit list of 8 curves. Four of them we've already seen. It's just that with this stronger assumption we're making, there are going to be 4 more. So that's part one. And part two is going to say that if E is semi-stable at 3 and rho E5 bar restricted to q squared of 5, sorry, just, well, no, just is irreducible, then rho E5 bar is modular. No. Well, yeah, so 8 curves, 8 isomorphism classes over C. So 8 curves and their twists. But you can find all these curves in the tables, and you just have to then check by hand in those examples that they're modular. In fact, there are only 3 isogeny classes here. So there are 3 elliptic curves. You have to look at the tables, check that they're modular, and then you can ignore these possible exceptions. Okay, and so the only change in the proof is dealing with this weaker assumption here. And so what's new is just the observation that if rho E3 bar, if the mod 3 representation is reducible, you just proceed as before. If the mod 3 representation is irreducible, but the restriction square root of minus 3 is not absolutely irreducible, then you can show that E contains 2 cyclic subgroups of order 3, which won't be rational, but they'll be rational and conjugate, but they'll be rational over a quadratic field. C3 prime defined over a quadratic field K. And I guess, well, and which is, so the set C3 prime will be stable under the Galois group of Q. Meaning if you have an automorphism, well, if it fixes K, it'll fix these 2 subgroups. If it doesn't, it may permute them. I guess if E3 was irreducible, it has to permute them because they're not rational. Okay, and so this leads one to different modular curves. So in the argument I gave before, you replace x naught of 15 by a new modular curve parametrizing, so I'll call it x prime. It's going to parameterize triples E cyclic subgroup of order 5 and a pair of cyclic subgroups of order 3, where this is a non-ordered pair. So for this triple to be stable under the Galois group is exactly the information that we get in this case. So a bad elliptic curve corresponds to a rational point of this, but in fact you can show that x prime is isogenous to x naught of 15. So it also has 4 rational points which are not cusps. 4 cusp points. And so again, to check these possible counterexamples, you have to look in the tables. You find them under conductor 338. And so you find curves there which you can verify have the right level 3 and level 5 structure. And of course, this is what you need to prove part 1. To prove part 2, you have to go back. Is it still there? No, I guess it's gone. No, it's over here. So one has to look at a different, one has to, in fact, take control both of these. So one has this other modular curve, which I call x prime of rho E5 bar. And, well, I'll just call it x prime of rho E5 bar, which is going to correspond to E prime phi, and again, pairs C3 and C3 prime. But you check that the, I confess I haven't checked exactly what the genus of this is, but it's at least 9. And so this only contributes finitely many bad points also. So you just have to ignore these others and you get the same result. Okay, that's all I wanted to say, except that as the final speaker who's actually attended this entire conference, I'd like to thank the organizers, Gary Cornell, Joe Silverman, and Glenn Stevens, for all the work that obviously goes into organizing such a large event. And I'd also like to thank the audience for making it such a success. Thanks.